Okay, so Essential Knowledge 5B3 talks about 3 ways in which a substance can change its energy. Heating and cooling, which we know changes the kinetic energy of the particles. Phase transitions, so melting or boiling, which are affecting the potential energy in terms of the intermolecular forces between the molecules, and chemical reactions. Chemical reactions change the nature of the bonds, and so that's a form of potential energy as well. That's stored energy due to the strength of the chemical bonds. So I want to talk about the heating and cooling curves for a substance because there's 2 things going on there. One, you're changing the kinetic energy when you change the temperature, but if we take a substance, say we take ice, and we started out at some very cold temperature. We take it out of the freezer and it's at negative 20 degrees Celsius. Well, we know that ice can exist all the way up to 0 degrees Celsius. So we can heat that ice up and its temperature will rise. We also know that ice can't exist above 0 degrees Celsius. So what happens when we reach 0 Celsius? Well, the ice melts. But we know that ice doesn't melt instantly. It takes energy in order to overcome those intermolecular forces between the water molecules and allow them to move more freely and turn into the liquid. Well, it takes energy to do that. So if on the x-axis this is time or energy added, because we have to be heating this thing the whole time. We have to heat it to get it from negative 20, the temperature of the freezer, up to 0, the temperature at which it melts, but we also have to add energy as we melt the ice. So that process is going to occur, energy is going to be added, but at that time at which we are melting it, the temperature is not going to change because we can't have ice above 0 Celsius, we can't have water below 0 Celsius. So until we get all that ice to melt and turn into liquid water, the temperature is actually going to stay 0 degrees. After we get all of the ice melted, so there's no ice left, there's all water, now the temperature can start to increase. But if you notice, I drew the slopes of these heating portions slightly differently because every substance, here's ice here, there's water here, every substance has a different, unique, specific heat capacity. The amount of energy that it takes to turn 1 gram of that substance to change its temperature by 1 degree. So water, the liquid state of H2O, and ice, the solid state, it takes a different amount of energy to change the temperature of those. So for ice, it's about 2 joules per gram per degree Celsius. For water, the specific heat capacity, 4.184 joules per gram per degree Celsius. So it takes twice as much energy to change the temperature of water by a degree than it does to change ice by a degree. Okay, so the slopes are actually, the ice is going to change faster because it takes less energy for every change in temperature. Okay, so we're going to heat water up, we're going to heat it up, we're going to heat it up until we reach the boiling point. 100 degrees Celsius. And now we know we can't have liquid water above 100 Celsius, at least at atmospheric pressure, and we can't have steam at any temperature below 100 degrees. So we're going to have another portion here that's going to be flat, at which the temperature is not changing, but we're still adding energy. That's the process at which we boil. Okay, so I'm going to label these phase transitions here. I'm going to label this one melting, and I'm going to label this one boiling. Okay, and again, we cannot increase the temperature anymore until all the liquid water has turned into steam. Once all the liquid water is gone, then we can start to heat the steam up, and then the temperature will rise above 100. Okay, so this portion here, we're talking about steam, and steam has its own heat capacity as well. It's about 2 joules per gram per degree Celsius. Okay, so really when we heat a piece of ice that's below its freezing point and we turn it into steam at above the boiling point, we're actually doing 5 different processes. We're heating the 3 different phases, the solid, liquid, and gas, and we're undergoing 2 phase changes, melting and boiling. Now, I drew these pretty close to the same length, but in reality it takes a very different amount of energy to melt ice than it does to boil water. So each of these different phase changes is going to have its own unique associated change in energy. So what I want to talk about is how do we calculate how much energy it takes to go through these different phases. Well, in these portions where we have just one single phase and we're changing its temperature, we can use the equation Q equals mc delta T. So if we know the mass that we're heating, we know the heat capacity of that particular phase that we're heating, and we know what temperature change we're going through, we can calculate the amount of energy it takes for that process to occur. That's Q. All right, but in this melting and this boiling portion, we don't have a change in temperature. We know we're still adding energy, but we're not changing in temperature, so this equation doesn't work. So we need a new equation to calculate the amount of heat. Well, the equation we're going to use is Q equals delta H times N. So delta H is a change in enthalpy. If we remember our reaction profile diagrams where we had activation energy and things like that, where we had exothermic reactions where they started with high potential energy, ended with lower, or we had endothermic where we started with low potential energy, we ended with higher, that change in the potential energy we symbolize as delta H, a change in enthalpy. Enthalpy is a little bit more complicated than that, but for now we can think about it as the change in potential energy. And those delta H's, if you remember from your last chemistry course, normally in kilojoules per mole. So if we know how much the enthalpy changes in kilojoules per mole, we can multiply by how many moles we're changing, and that will give us an energy. Now we got to be a little bit careful because usually these heat capacities are in joules per gram per degree, and these delta H's are in kilojoules. So for melting, the delta H, sometimes we call it the delta H of fusion, okay, is about 6 kilojoules per mole. Now it takes the same amount of energy to melt a mole of ice, 6 kilojoules, as you have to remove from a mole of water to turn it into ice. So either way you're going through this heating curve, the magnitude of that delta H is going to be the same. It's just going to be a question of, are you adding energy if you're going this way, or are you taking energy away if you're going this way? Okay, so for ice or water turning into ice, the delta H is 6 kilojoules per mole. So for boiling, on the other hand, we call that the delta H of vaporization to turn it from a liquid to a gas. That's about 40.7 kilojoules per mole. So actually, if you look at how I drew this, I drew it pretty poorly because if this is 6, that would be about 10. When in reality, it's supposed to be 40. So I really should have had this boiling, 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 boiling. And then we can start to raise the temperature. So this flat region should be a heck of a lot longer than this flat region because the amount of energy it takes to turn 1 mole of water into steam is way bigger than it takes to turn 1 mole of ice into water. Okay, but again, if we know these values in kilojoules per mole, we can just multiply by how many moles we're changing, and that'll give us the energy. Okay, so to do problems like this, what we really have to think about is what regions of this heating curve are we going through. So very simple cases, if you start out, say, with water at 22 degrees Celsius, and you want to heat it up to 80 Celsius, well, that's going to be a very simple calculation because you're only in one region of the heating curve. You're in this region where you have liquid water. You've got a temperature change, so you can just figure out the mass of water you have, the heat capacity of the water, and how much the temperature is changing. If you're going through multiple regions of the heating curve, like if you're taking ice at -20 and say you want to turn it into steam at some high temperature like 110 Celsius, then you're going to have to go through multiple regions of the curve. You're going to have to heat it up until you can get it to the point where it melts. You're going to have to melt it. Then you're going to have to heat it all the way up to the boiling point. You're going to have to boil it. And then you're going to have to heat that steam up to some higher temperature. I'll send it. Okay, so it's possible that you might have 1, 2, 3, 4, 5. I'll email it to you. Bye. You might have 5 different regions of the heating curve that you have to go through. So your Q total, your total amount of energy, might involve 5 separate calculations. You might have a Q for the ice, you might have a Q for the melting, a Q for the water, a Q for the boiling, and a Q for the steam. Okay, now the ice, the water, and the steam, those calculations are going to be in MC delta T. The melting and boiling, those are going to be a delta H times N. Okay, so this is as complicated as it can get. For a particular substance where you have all 5 of these calculations that need to be done in order to calculate the total. Okay, the things to be careful of is that each specific heat capacity is going to be different depending on the phase, and each delta H is going to be different depending on what phase change you're going through. Okay, the masses should be the same. The number of moles here should be the same. Okay, and then each of the temperature changes is going to be different as well. You got to be careful about that, because if I was going from, say, an initial of -20 up to a final of 120, well, the change in temperature for the ice is not 140 degrees, because we can't have ice above 0 Celsius. So the temperature change for the ice would just be 20 degrees. The temperature change for the water can go from 0 up to 100, so the water is going to go through 100 degrees of temperature change. So that's your delta T here. And then the steam is actually only undergoing a 20 degree temperature change. Okay, so that's one thing to keep in mind. You should never for a water calculation have a temperature change that's greater than 100 degrees. Because that's the maximum difference that water can go through at atmospheric pressure. It can only go from 0 degrees up to 100 degrees. Okay? Now,